We're in Module 12, comparing data that are what we call matched or paired up. Now we're going to be looking at the means of some values from samples. However, these means are going to be connected to what we call dependent samples. The previous lesson, 12.1, we did independent samples. The two groups were not connected in any way. We were comparing two independent groups. Examples of dependent samples would be like you have husband and wife data. We're comparing, do husbands make more money than wives, or are husbands taller than wives, or are husbands older than wives? We'd be comparing an individual husband with an individual wife and then looking at the average difference between all the different husbands and wives. Twin studies are another form where we study one twin and compare it to the other twin. They're linked together, the data, and we're looking at an individual difference between those units of study, right? To be twins. Sometimes we do pre and post tests of an individual. So for one person, we're looking at their before and after some intervention, that something happened. But because it's the same person, that pre and post tests are connected in some way. Or you test strength in the left hand versus right hand, right, from an individual. So it's the same person, and that's where this dependent part comes in. Every data value in one sample can be matched up to a data value in a second sample. They're linked together in some way by the individual or by some relationship, twins, husband, wife, teacher, student. There's, again, any types of way that you would be collecting data. An example of this is athletes and then wearing certain types of shoes and then running and then checking their times, right? It's the same person. So these times are connected. They're matched or paired up. And then we're going to be looking at the differences between those values. So here's a dot plot of where we compare with and without. And you can see the times. It looks like the yellow ones are faster than the green ones, right? And so that's what I would notice, right? Did the shoe help? That's what we would have to measure. And what we do is and we're not doing this by hand, the ARTISTAT will do it, but we're at least talking through it. So conceptually, you have an idea of what we're doing and how this is different than what we've done in the past. And so notice we'll find a difference. Without the shoes takes longer for 4 of them and faster for 2 of them. So these people ran slower with these new Vaporfly shoes. Is this enough data to say there is an effect, that those shoes somehow influence those individuals? And that would be the hypothesis test or confidence interval if we wanted to estimate the difference in times, or is there a difference? And you can see the distribution differences. There's 2 that ran faster with the shoe. Sorry, without the shoes, they take longer, and then there's 4 that run faster. If you look at that, that's what we see. Now, this is called a paired test, and when we run a paired test, the hypothesis is always the same type of, so it's actually the easiest one to write a null and alternative hypothesis. The null is always that the mean difference equals 0. The alternative is that it's not equal to 0 or greater than 0 or less than 0, that there is, and this D stands for before and after, or first or second, right? When you're comparing the two, in this case, it's a before and after design. So here's the example. Take a look at how we write it. There's your null alternative. It's a paired test. We're doing it at alpha 0.01, and you get a test statistic. Where do you get that? ARTISTAT is going to do this for us. So what you would do when you compare 2 means in the ARTISTAT, you're going to do dependent samples, and then you have this provide your own data. We're looking at the time. I have the before, right, with this is without, and then the after is when you're wearing the shoes. I'm going to enter in the data in group 1 and group 2. So with the data in, we can do a couple of things. We can compare the box plots. The green is without the shoes, after here yellow. So you start to see we had seen this difference distribution. In this case right now we have a confidence interval, so you could see, is there a difference? And notice there may be a slight difference because this 0 here, right? This 0 is not included But we're looking at, we want to be 99% sure, so we would do 99%. And then notice in the 99%, 0 is included. So we may not, at the 99% level of confidence, we would say that no, maybe there is no difference between those shoes. The shoes don't help, right? And so if we're going to do the significance test, then again, at the 99%, we're looking at this p-value, and we're saying a greater than, so I need to turn this test not to a two-sided, but a greater than. There we go. And then you get the test statistic and p-value. Again, that's a small p-value. However, we're trying a higher level of significance, right? And because we're at the 0.01, we want to be 99% confident with our conclusion. We would, in this case, reject the null hypothesis. Sorry, fail to reject. We do not reject it. So we say right now that there is insufficient evidence to conclude that the runners run faster while wearing the Vaporfly shoes, even though it's close, but it's not significant enough at the 99% or the 0.01 level significance. What would we do? Fifth step, is it random? We don't know. These are elite runners, so we don't know what that would mean. Sample size is small. We would like a bigger sample size. It's for sure less than 5% of all runners, that's for sure, but our sample size is too small. So again, we can still do the statistics. It's just we then have to be careful with the analysis and then our results. And if we were reporting this, we'd have to let people know that we had a small sample size.